In the second video from chapter 9, we saw how significant solvent can be in the nucleophiles and how that can affect an SN2 reaction. In this last video from chapter 9, right, part 7 here, we're going to look at solvent again and see how that can affect our reactions, okay? Because we know those ion dipole interactions in solution are critical. Yep. Then we will get one more named reaction at the end and finish with some synthetic applications. Okay. So what's notable and what you're probably already familiar with, because we've discussed it previously, is this idea of solvation. If something is charged and it's in a polar solvent, it becomes more stable, right? Because we have a polar solvent, water, for example, here, right, which has partial positives and partial negatives. Those interact with an ion, something that's charged, in solution by surrounding it with the opposite charge. If it's a cation, it gets surrounded with whatever is more electronegative and has that partial negative. An anion, it gets surrounded by those partial positives. Right? Both ion dipole interactions, both ways that polar solvents stabilize charge. Okay? So SN1 reactions, for example, or E1 reactions, aren't really prone to happening in a nonpolar solvent because nothing's present to stabilize that carbocation intermediate. Okay? But how can a solvent affect our reaction rate overall? Well, we need to think about our reactants. Okay? If we want a reaction to go forward, we want our reactants to react. Okay? But if the reactant that's participating in the slow step, the rate determining step, the RDS, that thing is charged. Increasing the polarity of the solvent decreases the rate of the reaction, okay? Because increasing the polarity of the solvent increases the ion dipole interactions with a charged reactant, meaning it's more stable and less prone to react. Okay? However, right, if none of the reactants that are participating in the rate determining step are charged, so everything's neutral to begin with, then increasing the polarity of the solvent increases the rate of the reaction because it stabilizes the intermediate, okay, and makes it easier to get there. So maybe that'll make more sense if we look at a reaction coordinate diagram. It's all about stabilizing charge, but where we're stabilizing the charge is important, okay? Because if the reactants are highly charged, then we're bringing them down here, making them more stable, and it's harder for them to react. Right? But if the transition state is charged, which it is, right, then increasing the polarity brings that energy down. Okay? So it's all about either the transition state tying into the rate determining step or the reactants themselves. Right? A polar solvent is always going to stabilize things that are charged. Okay? Here, we're stabilizing the reactants. Those are more highly charged than the transition state. Here, right, the transition state, we don't have charged reactants. Now we've got a charged transition state. Bringing that down makes it an easier energy barrier. Okay, so what are you stabilizing? If it's the reactants that are charged and those are being stabilized by a polar solvent, you're less reactive. If not, then it's the transition state that's charged. You're stabilizing that, lowering the energy barrier, speeding up the reaction. Okay. So now consider our SN1 and our E1 reactions. Okay. The rate determining step is going from, right, our reactant, our alkyl halide in chapter 9 to the carbocation intermediate. That's the slow step, okay, the rate determining step. And we know that the charge on the transition state, which is approaching the intermediate, okay, labeled the product here, product of step 1, intermediate of the overall reaction, that's greater than the charge on the reactant. Okay? Reactants are neutral. Therefore, for SN1 or E1 reactions, the transition state is stabilized by a polar solvent. So increasing the polarity of the solvent makes the reaction faster, which is seen on the next slide here. Increasing polarity, faster relative rate. And so that's for SN1 or E1 reactions there in table 9.8. Okay, what about SN2 or E2? In that situation, we need to look at what's acting as our nucleophile or as our strong base, right? Because we need a strong base for an E2 reaction. Those things, as we've said previously in this chapter, are typically negatively charged in order to make it a good nucleophile or a strong base. Okay. So if that's the case, right, substitution reaction up top, elimination reaction on the bottom, but both of those are using a charged reactant, right? They're bimolecular. That hydroxide is involved in the transition state. Okay. In that situation, right, increasing the polarity of the solvent stabilizes the reactant even more than it does the transition state. So increasing the polarity of the solvent slows the reaction here. Okay. So yes, a more polar solvent does stabilize that transition state like it did before, but not to the same degree that it stabilizes the reactant. Okay, so polarity is not great here, but we do need to have some degree of polarity in order to dissolve these things to begin with. I can't use a nonpolar solvent for an SN2 or an E2 reaction. We discussed that in video 2. Right? So what do you need to use? We need to use an aprotic polar solvent in order to dissolve our charged nucleophile and our alkyl halide and let the reaction go to begin with, but not to hinder the reaction overall. So this slide summarizes what solvent should be used. SN1 or E1, go ahead and use a polar solvent. The more polar, the better. SN2 or E2, typically those are going to be charged nucleophiles in order to get the best reaction. Okay? So then you're going to use an aprotic polar solvent, as we just mentioned, something like DMSO or DMF. Okay? If you happen to have an SN2 or an E2 reaction with a neutral nucleophile, that you can do in a polar solvent. Okay, but these are less common because then they compete with SN1 or E1. So solvent choice is important. Key idea when you're designing a synthesis. Okay. And on that note, we do get a new reaction here in chapter 9, a synthetic application. Okay. How do I use these reactions, get a good yield? Well, I get one named reaction here. It's called the Williamson ether synthesis. Okay. Shown here on slide 144, the Williamson ether synthesis, named after Alexander Williamson. Okay. If something's a named reaction, typically pretty famous, so it's a good thing to star in your notes, right? That deals all their reactions from chapter 8, the Williamson ether synthesis. These things are notable reactions, things you definitely want to know come test time. Okay. So what is the Williamson ether synthesis? It's a reaction between an alkyl halide and an alkoxide ion to form an ether, right? Kicking off an alkyl halide as the leaving group. Right? Question is, how do I make the alkoxide ion? Because you're not just going to grab that off the shelf. You get that by reacting an alcohol with sodium hydride. Okay? This dissolves in solution to Na plus and H minus hydride. Right? That H minus is basic enough to pull the hydrogen off of the alcohol, right? Form H2 gas, and leave behind your alkoxide ion. So let's look at some variations of the Williamson ether synthesis. Okay? You can start with an alkyl halide, introduce different alkoxides, right? Butoxide, propoxide, things like that, and boom, you make ethers of whatever length you choose. Multiple possibilities, but you've got to keep in mind reactivities and make good choices when you're designing a synthesis. Okay? These will both be fine because Williamson ether goes via an SN2 mechanism. Okay? That's why we're using primary alkyl halides, for example, and good nucleophiles. But what if I wanted like a tert-butyl group on my ether? Okay. Well, if I'm trying to make an ether, right, my tert-butoxide ion now, that's not as good of a nucleophile because it's sterically hindered. Okay. So now I get a mix of the substituted product, the ether, and the elimination over here. However, I have to do that because if I make the alkyl halide tertiary in order to get that on my ether, right? Now it's a tertiary alkyl halide. Those can't undergo SN2 reactions. So even if I react it with ethoxide, I only get the elimination in that group. Okay, so that's a key takeaway for the Williamson ether synthesis. It goes via SN2. If you have steric hindrance in your ether, you better be doing it on the alkoxide ion. You can't do it on the alkyl halide. Okay. Now, if you wanted an alkene, then you would do that, which is important to pay attention when you're designing a synthesis. Control the conditions to favor substitution or favor elimination, depending on what you want. If you want to do an elimination, use the more sterically hindered alkyl halide you can get, right? Maximize the elimination. In this situation, right, alkyl halide, secondary, you get the elimination as your major product. Alkyl halide that's primary, substitution as your major product. If you wanted to specifically do the elimination, you could make it even better by using a bulky base like DBN or DBU, or increasing the temperature. Okay. So it's lots of factors from chapter 9 to make sure you're paying attention to. Okay. Even the base itself, if we're designing a synthesis to do an alkene, the strength of the base is significant. Right? I want to make this go via E2 only. Okay? If I use a weak base down here, right, then I get a mixture of my elimination and my substitution, because I've got E1 forming my alkene and some SN1 that's forming my substituted product, the ether. Okay, so pay attention to the base. A strong base encourages E2, and you'll only get the elimination because I can't do SN2 for a tertiary alkyl halide. Okay, so stronger base encourages E2. So one note to finish up on with regard to the Williamson ether synthesis and our reactions from chapter 9. What if we have multiple functional groups in the same molecule? That's called bifunctional, two functional groups, right? And that gives us multiple possibilities for how to react. They can continue to be intermolecular, right? But we can also have intramolecular reactions where a molecule is reacting with itself. Right? Look at the difference up top here. Reaction between two different molecules. That's an intermolecular reaction. Okay. But on the bottom here, I can also have an intramolecular reaction, right? Intramolecular, just like intramurals, right? Intramurals are within the same college. Here, an intramolecular within the same molecule, right? I can bend around, attack itself, kick off the leaving group, and form a cyclic ether there called a furan. So how do I determine, in that situation, which one of those predominates? Well, it depends on two factors: concentration first and size second. Okay. So how about concentration? If that molecule is at low concentration, that's going to favor an intramolecular reaction because it's just a game of probability. Those two functional groups that are on the same molecule have a better chance of just twisting around and finding one another than they do finding another one. Right? It's like being lost in the woods when they're at that low concentration. But if you have a high concentration, it's like being in the middle of a concert, right? You're bumping into people all the time. That is going to favor a reaction with another molecule, an intermolecular reaction. So that's factor number one, concentration. But size is important as well, size of the ring. Okay? I'm never going to do an intramolecular reaction to form a 3 or 4 membered ring. Those are too strained, right? We've talked about that in the past. We don't like 3 or 4 membered rings. Too high of an activation energy. And if my rings get too large, 7, 8, 9 members, right, then the groups are too far apart. Right? They've got a low probability of encountering one another. So if and only if you're going to form a 5 or 6 membered ring, then that's going to favor an intramolecular reaction. See here, I've got 1, 2, 3, 4, 5, 6 members. Here, 1, 2, 3, 4, 5. I have 5 and 6. If you can form those, then you'll do that via an intramolecular reaction, right? 2 intramolecular SN2 reactions over here. Right? If not, then it's going to be intermolecular. So 2 factors to pay attention to. If you have something that's bifunctional, it can have the nucleophile and the electrophile in the same molecule. it'll react with itself at low concentration to form 5 or 6 membered rings. Otherwise, it's just going to continue to react with other molecules as we've already anticipated. Okay. So that concludes the new material from chapter 9. The chapter finishes with synthetic applications, which again, I will encourage you to go through and do these for review. You've got the problems and then the answers in each situation. And I do that on purpose, give you a blank slide and then give you the answer, because these are great problems that tie in reactions from chapter 9, chapter 8, chapter 7, chapter 6, all together. A great way to review all of these important concepts from organic. So take the time, practice working on these syntheses, and then you'll be well prepared for the next exam.